Good morning, this is the 15.6 video. It is on surface integrals. This is page 880. They give you a little bit of an introduction here. And so what we're going to be doing is integrating over surfaces as opposed to integrating over curves. So this is, it says here, an extension of the idea of a line integral. So line integrals I'll just show it to you here. Line integrals were single integrals over some curve C. Surface integrals are going to be double integrals over some surface S. And so just like in previous sections when we were doing line integrals, the curves could be made up of several pieces. So if you don't know what I'm talking about, you can look at number 16 on page 833. It's you have like curve 1, curve 2, curve 3, that kind of thing. So surfaces can be the same thing. They can be made up of several pieces. So for example, this example 2 here, you can see this surface is actually made up of 6 different sides. And so that's the same idea as in curves, but again, now they're going to be surfaces. Sorry, I forgot to clean my screen before I started. Okay, so we're going to be working with the same kind of things as we had before. These parametric equations that are functions of 2 variables. And then just like in the previous section in 15.5, we're going to have some things that we can define with parametric equations and some things that we're going to have to do implicitly. There is also explicitly, but we're not going to do that. So parametrically or implicitly are going to be the 2 that we're going to do. So these are the surface integrals. So you can see it's double integrals over surfaces. We're going to have these same parametric equations. For this one, we're going to have that same magnitude of the cross product that we had before. For the implicit ones, we're going to have this same, this p vector, remember from last section, and the magnitude of the gradient vector, the absolute value of the dot product. So it's the same thing that we were doing in 15.5, just sort of a level up from that. So it's an extension of what we were doing before. And then down here, this is page 881, it tells you that depending on the situation, there's different applications of these surface integrals, but one application is if the function g is just a 1, then remember, I don't remember what chapter it was in, but remember from before, if you have a double integral of 1, then it represents area. So it's the same thing here. So if the function g is a 1, then what you're finding is area. Okay, so we're going to look at some examples. This is page 887. Actually, first here I'll show you. These are the same things I just showed you, but if it's easier to have them kind of without all the extra fluff, then here are the 2 formulas, parametrically, implicitly, and again, the fact that you can use these to find area if your g is 1. All right, so we're going to start with number 2. So number 2, here's my function. I guess it would help. Look at this one piece at a time. Okay, here's my function. The function is z. It's over this cylinder above the xy plane. X is staying between 1 and 4. So for the picture, I drew the whole thing because it was too hard for me to draw just the top half. So here's the whole cylinder, but you want just the part that's above the XY plane. I'm not talented enough to draw things very well, but it would just be the top half of that. So like I probably could have done it. I just didn't want to have to white it out when I drew the whole thing. Anyway, cut it off, here, and so it would just be the top half. So this is the plane x equals 4. This is the plane x equals 1. It's cutting off the cylinder so that you just have a piece of it. So we're going to solve this for z. So subtract the y squared, take the square root of both sides. Since z is positive, we don't need the plus or minus. Now we're going to do the parameters. I don't know if we did this in the previous section, but this is a one that you can do. You can just let x be x and y be y, and you're using x and y as your parameters. But because you can only have 2, you can't have z, and so by solving for z, you can see how here z is a function of y. So it is just 2 parameters. So x is x, y is y, z is this, x is between 1 and 4, and then y is between -2 and 2 because over here would be where y is -2, over here would be where y is +2. So it's both sides, the left side and the right side, but it's only the top half. Okay, so this one we're going to do, let me turn to that page with the formulas. This one we're going to do using this formula, so we need the partial derivatives. Okay, so partial with respect to x, partial with respect to y. This one I just cleaned it up a little bit here. And then we're going to do set up the cross product. Okay, so then in the cross product, there's all the pieces. Simplifies down to just this. We do the magnitude, simplifies down to just this. Okay, so that's the magnitude of the cross product. So now here's my formula. This is the same formula that was in the book. But you can't use the z for your g. This was what your g originally was, but you can't use it because you have to have just x's and y's now. And so you have from up here that z is this. So g equals z becomes g equals this, since z is equal to this. Sorry, trying to turn the page. Okay, so here's your double integral. You've got the g, you've got the magnitude of the cross product, and you can do x or y first, it doesn't matter. So now it's just a basic integral because these cancel, so these will cancel and it just leaves you with 2. Okay, so this is a simple integral to integrate, so you get 24. All right, so let's try another one. This is number 4. This one we're actually going to use spherical because we have a sphere. So it's the sphere, I didn't draw this one, but the sphere centered at the origin, radius a, but only the top half of the sphere, so it's a hemisphere actually. So for my parameters, I'm going to use phi and theta. X squared plus y squared plus z squared equals a squared becomes phi squared equals a squared, so phi is a. And then these are on page 810 for these formulas. And so into each one, wherever you have the, did I say phi or rho? I don't know. Now I'm wondering if I said phi. It's rho squared equals a squared, rho equals a. I don't know what I said. But anyway, so you substitute in for the rho, you put a's for all of those. So here's your parametric equation. Since the z is positive, then the phi is going to stop at pi over 2 because it's going to stop when it hits the xy plane. No restriction on the theta, so it's 0 to 2 pi. So you set up your cross product. This one's kind of complicated. It's got a lot of pieces, so I, j, k, here's all my pieces. All right, and so up here, here's the simplified version. Every time you have a cosine squared and a sine squared, you can factor out whatever's in front of it, and then the cosine squared and sine squared, of course, are 1. So it simplifies down to here's my cross product. So I'm doing the magnitude of that. Again, when you have a cosine squared and a sine squared, factor out what's in front, and it becomes 1. Here's another sine squared plus cosine squared. And so it simplifies down very nicely to just this. And then here was my g, but I can't leave it as z because I've got to change it to spherical. So z is the same thing I have from here. Z is the same thing as a cosine phi. And so in place of the z, I'm going to put an a cosine phi, but then I've got to square it. So here's my g, here's my magnitude of my cross product, and then here's my bounds. This is a u substitution. And then simplifies down. Oh, my answer's on the next page. Hold on, I'll give you 1 second to look at this work. Okay, so simplifies down to this. So this is my answer. All right, and so since we've done spherical, it only seems fair that we should do cylindrical now. So number 6 is cylindrical. And this again, I know I'm going through this kind of quickly, but it's very similar to what you were doing in 15.5, except in 15.5, I think all of your g's were 1, and now you just have g's that are functions. That's really the only difference so far, is that my g's are functions instead of 1. So that's why I'm going through this kind of quickly. Hopefully, of course, I guess since it's a video, you can pause it and go through it as slow as you want to. You can put me on slow motion. That's how I sound on slow motion. I don't know. Probably sound, I don't like the way I sound in normal motion, so who knows how I sound in slow motion. Maybe it's better. I don't know. Okay, here is number 6. And this is my function. I don't know why they're calling it f here instead of g. Who knows? This is my function though. And it's over this. And so I'm going to change this to cylindrical. So that's what this is about. But it's over this where z stays between 0 and 1. So in cylindrical, my parameters are r and theta. So x is our cosine, y is our sine. And then here, x squared plus y squared is r squared. So z just becomes r. So here's my x, here's my y, here's my z. Notice now I just have r's and thetas. And then because z is the same thing as r and z stays between 0 and 1, that means that r has to stay between 0 and 1. And then because I have no restrictions on my theta, it's between 0 and 2 pi. So find my partial derivatives. I put them in my cross product. I evaluate my cross product. Again, when I have cosine squared and sine squared, I can factor out what I have in front of it. And that becomes 1. So here is my cross product. Then I'm going to do the magnitude of it. Again, factor out. And so it simplifies down to just this. All right, but then again, remember I have this function. I have to change that also, so I'm going to do that next. This function is in Cartesian. I need it in polar. So z is the same thing as r. X is the same thing as r cosine, so it becomes this. So here's my function, which normally is a g, but here they're calling it an f. And here's my magnitude of my cross product. You cannot integrate a product, so you have to distribute. And so that's just a basic integral. I'll just show it to you. Ends up being 2 pi squared, so 2 over 3. Now I have a more complicated one that I'm going to show you in a minute. I'm going to show you number 12 first, and then I'm going to go back and show you number 10. It's somewhat complicated, more complicated than something I'm going to give you, but because there's so many physics applications in chapter 15, just in case you would see something like this in physics, I do want to show it to you, but it's more complicated than something I'm going to give you, so I kind of have it separated out. But I haven't had physics in 200 years. And so 200 years ago when I took physics, it wasn't really 200 years ago, but it for real was probably 20 years ago. I don't remember what all you needed, and I only took 2 physics classes because that's all I had to have for math. And so I just try to show you everything I think you might possibly need so you're prepared for whatever comes up in physics. So I am going to show you number 10 in a minute, but we're going to start with number 12 because it's a lot easier. Okay, so number 12, you have, this is your function, x, y, z. Your surface is a rectangular solid. So here, I didn't draw it in the xy plane because depending on the values of a, b, and c, who knows where it's going to be. So I just drew it just sort of floating out on its own. But the x's are between negative a and a, y between negative b and b, z between negative c and c. So notice it makes 6 regions, which you normally would have to do all 6 separately. But thankfully here, because of the fact that these are, because of the nature of this, I'll show you in a minute, thankfully you're not going to have to do all 6 separately, but you start by assuming you're going to have to. So region number 1, so you have 6 regions, x equals a, which would be here, x equals negative a, which would be the back, y equals negative b, which would be the left, y equals positive b, which is the right, z equals positive c, which is the top, z equals negative c, which is the bottom. So we're going to start with the front. This is the front, x equals a. And so in general, I guess it would help if I told you, we're switching formulas now. That would be helpful. We're going to start using this one because we're not going to do it with parametric equations. We're going to do it implicitly. So if we're going to do it implicitly, g is the function, and then, g is the thing that you're integrating. F is that function, remember, that equals c. So f is some function that equals c. So f is some function that equals c, and so here, this is some function that equals some constant. Don't get this c confused with this c. They just mean constants. It's totally different c's. But here's a function equal to a constant. So my f is going to be that x. My g they gave me up here. And so into the function g, I'm going to substitute this in. So x is a. So everywhere I have an x, I'm going to put an a, so it becomes this. And then x equals a is a plane that's parallel to the yz plane. If a is positive, it's in front of the yz plane, obviously. And so parallel to the yz plane, the projection would be in the yz plane. And so your p, your unit vector, remember your unit vector, p has to be normal to the plane. And so I would be normal to the yz plane. So the yz plane, I, is going to be your p. Okay, so I need my gradient vector. So here's my f up here. And so the partial derivatives would be 1, 0, 0. The magnitude of that obviously is 1. Do the dot product between that and my p, and I get 1. So I'm substituting in my g, which is this. I'm substituting in my magnitude of my gradient vector, which is this. And it's supposed to be absolute value of my, hold on, let me fix it. It's supposed to be absolute value of my dot product. Okay, so that should have absolute value bars on there. Okay, so notice it's a function of just 2 variables. You should not have 3 variables here, just 2. And then here's my region. So z is between negative d and d. Y is between negative c and c. So this is a basic integral. But notice what happens because of this, the negative c to c. Well, actually, it was because of the negative d to d originally. But because of this, it's going to end up being, because of the symmetry, it's going to end up being 0. And so if you tried that with any of the other 5 regions, the same thing is going to happen because they have the same, negative a to a, negative b to b, negative c to c, negative d to d, whatever it was. I don't even know. Why do I have... Whoops, I did that wrong. It's supposed to be, these are supposed to be b's. Hold on, let me write myself a note. Fix number 12. Okay, it was supposed to be y was between negative b and b, and z was between negative c and c. I'll fix that for when I post it on Angel. But if you want to go ahead and fix it, it doesn't really matter. They're just constants. But This is supposed to be negative b to b, and this is supposed to be negative c to c. So sorry about that. Either way, it's still 0. It doesn't even matter, but I will fix that in my notes. Okay, so anyway, so you don't have to do the other 5 because they're all going to be 0. They're going to be 0 also. All right, so while we're talking about this one, I am going to go ahead and show you number 10 now, and then we'll come back and finish the section. But number 10, again, is not something that that I'm going to give you, but just in case you need it in physics. So here you have your function is y plus c, and your surface is this like rampy kind of wedge-looking thing. You're in the first octant. You're bounded by the coordinate planes and the line x equals 2, which is here in the front, and y plus c equals 1, which is this sloped plane. So notice it's made up of 5 pieces. I drew it here so you can see you've got the front and the back. You've got the left, the bottom, and this is not really the right side, but it's this sloped side that's kind of on the right. So what you would have to do here is you would have to take it one surface at a time. And so for the front, x equals 2, so that's going to be your f. Your g stays the same for every surface except that, or starts off the same, but then you've got to change it. So if x is 2, you would plug in a 2 for x. You don't have any x's, so you can't do that. But then this region is parallel to the YZ plane. So you're going to use I for your p vector. So you would find the gradient vector, magnitude of the gradient vector, dot product. And so you end up, I don't even know, where are my notes? Okay. Sorry, I'm trying to keep my notes all straight, trying to figure out where everything is. Okay, so you're going to look at your region. Here's your region in the YZ plane. You're going to take this line and solve it for z. So z is between 0 and the line, y is between 0 and 1, putting everything where it goes. I forgot the absolute value bars again. I guess because it keeps being positive. I don't think about it. Okay, anyway, so you would integrate. This is a basic integral, so I'm not going to go through it. Make sure here you do FOIL. You've got to do FOIL. And that would be your integral. So I just highlighted this because I'm going to save it because we're going to take all 5 of these answers and add them together when we get finished. So I just highlighted it so I could find it again later. All right, region 2, this is the back. So looking here, it's that back triangular piece. There, x equals 0 because you're in the YZ plane. So your f is x again. Now, x is 0, but again, there's still nowhere to plug in for the x. This is in the YZ plane, so your p is 1. So this is all the same kind of stuff. Same region, same everything. So you get 1/3 again. All right, now for the left side. If you look at the left side, it's this rectangle here. Okay. So the left side, that's where y is 0. So your function is y. Now in place of the y into the g, you're going to put a 0. So that would be z for your g. This region's in the xz plane, so your p vector is going to be j. Then you find your gradient vector, magnitude of the gradient vector, dot product. I still forgot my absolute value bars. I don't know why I keep forgetting my absolute value bars. All right, there we go. Basic integral, and you get 1. Oh, and this was the region in the xz plane. Okay, now for the bottom. So if you look at the bottom is this rectangle here. You can see it's in the xy plane. So for the bottom, because it's in the xy plane, z is 0. Your function is z. You plug in a 0 here for the z. So your g is a y. It's in the xy plane, so your p is k. Gradient vector, magnitude of gradient vector, dot product. Still no absolute value bars. Okay. And so this is the same idea as region 2. Notice this is xy plane, or not region 2, region 3. This is the xz plane, but it's the same principle. So I still end up with a 1. And now for the kind of tricky one, for that sloped right side. So that sloped right side, that was this sloped plane here. So for this one, your plane comes from this. So solving for z, you get this. Well, here, I don't need that yet. Let's look at this one. This is my function, my g, because it's, I'm sorry, not my g, my f, because f is equal to a constant. So my f is y plus c. And then for my g, it was y plus c, but now I need that. I'm going to solve that for z and plug it in. Or you could have just substituted in a 1 because y plus c is 1. Either way, your g is a 1. All right, so for your f, here's your f. Up here, you're going to do the gradient vector and then the magnitude of that. But now for your p, you're not actually using the sloped plane. You're using the projection of the sloped plane. So you're projecting this sloped plane into the XY plane. It's like the shadow we were talking about before. So I shaded it here like a shadow. So that would be in the XY plane. It's this rectangle. So since it's in the XY plane, I'm going to use K for my P. So I do my dot product. Again, I forgot my absolute value bars. I remembered it here. I forgot it here. Okay. Anyway, so you can't have y's and z's in the xy plane, but because y plus z was 1, you can just substitute in a 1 since y plus z was 1, and you can just use 1 for your g. So here's my g, my magnitude, my dot product, so very basic, and I get this. Oh, I didn't highlight it. Hold on, let's highlight it. Okay, so I get this, and then now you're going to add up all 5. I have them all highlighted, so I've got the 1/3, the 1/3, the 1, the 1, and now this one. Add them all together. That's the 5 individual surface integrals, and so this is the whole thing. Okay, so this is the sum of all 5 of them. So that one is obviously more complicated than what I'm going to give you, but I just wanted to show it to you in case you run across something like that in physics. All right, but now let's go back to something like I would give you. So this is number 16. Hold on, let me make sure. Okay, this is making sure my directions didn't change. They didn't. So here's my G. I've got a surface. So here I'm still using that implicit formula. So notice this one, it's not equal to a constant. Your F has to be equal to a constant. So to get it equal to a constant, you've got to move everything over to one side, and then your constant is 0. So notice I had to move this Z over with the X squared and the Y. So this is actually my F. Your F has to be equal to a constant. So if it's not already equal to a constant, you got to make it equal to a constant. Okay. Ow, sorry, my back hurts. Okay, I was trying to fix it. It didn't fix it, but I had to try. Okay, so here is my, where was I? Okay, here's my F. Sorry, I get distracted. My back pain distracts me. All right, I can do this. So here's my F. I'm going to do the gradient. Here's my gradient. Here's my magnitude. And then here, oh, I didn't show the work. But the projection, you would do the projection of this, and so the projection would be in the XY plane. And so if the, sorry I didn't show that, but the projection is in the XY plane if you draw this. And if you draw this, notice because it's saying here for X is between 0 and 1 and Y is between -1 and 1. So anyway, that's why I'm using K for my P, because you're doing, again, the projection. And so do the dot product and I get -1. So here I remembered my absolute value bars, thank goodness, because that would have been bad since it was negative. So here was my G, it's just X. Here's my gradient vector's magnitude. Here's my dot product. I'm integrating with respect to X and Y. So make sure to make that positive. And then this is gonna be integrated first with respect to Y, so I just stick a Y on the end. And then it's gonna need a U sub. So next page, here's my U substitution and integrating, and I get this. So again, this is just a continuation from 15.5. It's just that now you have to deal with your function G. And so with your function G, just remember to change it to the 2 parameters that you're using, or the 2 variables that you're using if you're doing it implicitly. And I think that's everything. So if you have any questions, send me an email.